Hello.
How are you today?
Fairly good.
Good. Okay, I got the two documents that were emailed to me, and I'm happy to go over integration by substitution. But before we do, I would like to revisit a problem we had a couple of sessions ago that I had some confusion on, and I felt like it was important to straighten out what I had said. Do you hear all that background noise?
A little of it, not much. It's fine.
Do you have a speakerphone by chance? Could I call you?
Not really.
All right. Okay. We'll see if we can handle all of this audio noise that I seem to be picking up.
Fine.
Okay. Remember the problem we had where the ladder was resting up against the wall and a boy was pulling the ladder at the bottom to the left at some rate?
Yes.
And the problem was find out what dy dt was, or something like that.
Yeah.
And where I had difficulties that day was presuming that because the ladder was being pulled to the left, that dx dt was negative. And that's where I was wrong. The sign on dx dt has to do with whether x is increasing or decreasing. When that boy pulled the bottom of the ladder, x was going to increase. So dx dt was going to be positive. Positive 2.
That one.
I was confused because it was going to the left. And on some problems concerning velocity, to the left is negative, to the right is positive, up is positive, down is negative. So it was real hard for me to reconcile that on this problem. I kept thinking that dx dt had to be negative 2 because it was going to the left. But it's not a question of whether it's going left or right. It's a question of whether it's getting bigger or smaller. What would the sign on dy dt be as the kid pulled the ladder?
Negative.
Correct. So that's what it has to do about. And I don't know if I ever gave you the police chase where the police, part of my confusion stemmed from this problem, where you have a police car going 60 miles per hour chasing bank robbers who are going this way at 50 miles per hour. And the police car has to get to the intersection, but they can put a radar on the chase car so they know how fast DDT is. They know how fast they're going. The question is how fast is the car going? Well, this is a related problem also. And the reason I was always confused is because in this case, dy dt is getting negative as it goes down. And dx dt is getting positive as it goes to the right. So I thought the thing that ruled it was the direction it was going, and it is not. What rules it is whether it's getting bigger or smaller.
That makes sense.
All right. Let's look at these problems here. In general, how do you feel about integration by substitution?
Not very good at the moment.
All right. Let me minimize this for a minute. It's really pretty simple. Let's say I wanted to integrate that. You might think that you could apply the power rule and say 8x squared minus 1. I'm going to add 1 to the numerator, divide by the new exponent, and that would be it. But if you took the derivative of this, you would have to apply the chain rule. So not only would you get that, but you would get a 16x also. Got it?
Yeah.
Okay. So, if I'm going to integrate something complicated like this, it would be extremely helpful if I had a 16x right there. Let me show you why. We're going to use something called U substitution. And probably the best way for you to really get this is just to memorize the method. Don't worry about conceptually understanding it so much. Just memorize the method. There's two kinds of U substitution. I'm going to go over one of them now. What would be the most logical thing to let U be?
The what's inside the square root, the x squared minus 1.
Exactly. What we're going to do is we're going to turn this integral, which is now an integral in x, we're going to turn it into an integral in u. Let me show you how we're going to do that. If u is equal to square root, then du dx is equal to what? This is one of many integration problems that requires as much differentiation as it does integration. What's du dx? Take the derivative of this.
The derivative of that is 12x, or not 12, it's 16x.
Which makes du, thinking of differential equations, it makes du equal to this. Do you see how I got that?
Yes.
Okay. So it makes dx equal to du divided by 16x. You see how I got that?
Yep.
So now I'm going to take this integral and rewrite it as an integral in u. Instead of dx, I'm going to write that. And now a magical thing happens. We get rid of the 16x, which is necessary because you cannot integrate an integral in u if there's a variable in x in there. So we end up with this, which is easily integratable. Now we go back and we substitute what we let u equal to. Well, u is equal to 8x squared minus 1. And there's our answer. And if we take the derivative of this, you will notice we get applying the chain rule times 16x, which is what we started with. That's what we were trying to integrate. So, the net lesson, the most common kind of integral is one where you have a composite function multiplied by the derivative of the inside. Notice that that's exactly what we had. We had the square root of a composite, that's a composite function. It was multiplied by the derivative of the inside. And when you use u substitution, you know that this dx is always going to have in the denominator the derivative of the inside. As we do some of these today, we'll notice that over and over and over. When you let u equal to this, and you find du, and then you define dx, it's always going to have this part in the denominator, which perfectly cancels out with it. And then it allows you to take an integral of u that you know how to do, as opposed to taking an integral of x that we didn't know how to do. And just a word about integration. I probably have told you this before, but differentiation had beautiful things like the power rule, the product rule, the quotient rule, the chain rule, and you could pretty much differentiate any function. You still there, Chase? Chase, you back?
Yeah, so I bumped something on accident.
All right. So what I was saying was that differentiation has all these neat rules that allow you to differentiate pretty much any function. Integration is not the same. You might think it should be, but it is so much harder to integrate than it is differentiate. This is kind of the reverse of the chain rule. Instead of multiplying by the derivative of the inside, we are going to end up having to divide by it. But you'll get the technique. What you want to look for is this. You want a composite function multiplied by the derivative of the inside. All right, let's look at these problems. Is there one you want to start with? You want to start at the beginning?
I guess that works.
Okay, this is a variation of the one I just did. The only reason I put it in square roots is because there would be another way to do this one. Notice the easy way to do this without using u substitution would be to merely expand it. In other words, I could square this, I could multiply it all by 16x, and I would have a fifth degree polynomial, which I could separate into 3 integrals and apply the power rule on each one. However, if I do this, which is what I did, put the square root under that, now I could not do that other thing. To solve this, I have got to use integration by substitution. And I did. Now, I can use integration by substitution here also, and I would let u equal the same thing, but it's going to be u squared instead of u to the 1/2. So, let's skip 1 and go to 2. I don't know if you have to do just the odd ones or what.
For this one, I'm not sure. I don't remember which one she said.
All right, well, let's just do them all. This is worth putting a lot of effort into U substitution. It's real important you know this. What am I going to let U here? And let's just go through the sequence of how we're going to do it. Always figure out what U is.
So again, U would be x to the third plus 1.
What's du dx?
Du dx is x squared.
3x squared.
Oh yeah, 3x squared.
Which makes du equal
3x squared dx.
And makes dx. We really need to solve for dx because we're going to have to substitute for that dx. So dx is equal to what?
Du divided by 3x squared.
All right. Now we're ready to write it as an integral of u. I'm going to leave the x squared there for a moment, and there is a little bit of a shortcut that eventually I'll show you here, but I think it's very important to do a couple of problems in full. And in place of dx, I'm going to write
Du over 3x squared.
Okay. Now, notice that what's in my denominator is not exactly what's over here. This is x squared, this is 3x squared. But the important part is that it got rid of the variable. So now I have an integral of the square root of u over 3 du. Well, probably the best thing to always do when you're integrating is take out constants.
You just integrate the constant factor.
Times 1/3, which is 2/9 times u was x cubed plus 1. In other words, we go back and reverse substitute. And there's your answer. Same pattern every single time. Okay? Let's have you do it on the next one.
Okay.
Hold on. U equal to?
U is x squared plus 1.
What's the next step?
The dx du equals
Du dx.
oh yeah, du dx equals 2x, which then du equals 2x dx, and then dx equals du over 2x, and then we would rewrite the equation with du over 2x where dx is. So we have x over u to the 1/2. And now we have an x that we cancel with the, yeah. And then, we have the du, we pull out the 2, we move the constant, or 1x, yeah, it's
Pull out the 1/2. It's 1/2, not 2.
Yeah, yeah.
Okay, and then we have...
And then we negative 1/2 u, and then we just integrate that, so we get...
Using the power rule. Go ahead.
U, so that's 2/3 u to the...
Hold on.
Yes.
Add 1
yeah,
to the x bar.
negative took me up there.
No.
That's
When you
1
add
half.
1, it gets 1/2. And then divide by the new
Yeah.
exponent, which is the same as multiplying by 2.
Yeah, 2.
Which
The
gets
negative
rid of
should be
this
up there.
1/2.
I forgot that it was negative when we moved it up.
So that's our
So
answer. Because that 2 we multiply by gets rid of the 1/2.
Yes.
Okay, good. So the general rule we're looking for, and what you're going to end up having to do eventually, is they're going to give you an integral of a function. They're not going to tell you that you need to integrate this using substitution. You're going to have like 4 or 5 different possible methods you can use. One is substitution, one is by parts, one is partial fractions, one is by trig substitution. There's all kinds of different techniques you're going to learn for integration. So this chapter is all about integration by substitution. So what you're looking for when you're looking to see whether something qualifies for integration by substitution, for instance number 3, is the derivative of the inside going to cancel out with this x? And if so, it qualifies for integration by substitution. Let's look at 4.
Get that. So what does u equal? I'm trying to decide what
Let's go back
to
a
make u
moment.
to cancel
Hold
out.
on. Let's go back a second. There's some integrals you should learn. What's that equal to?
Negative cosine of 5x.
Divided by 5. Take the derivative of that. You get sine of 5x over 5 times the derivative of the inside. Cancels out with that 5. So you end up with sine of 5x. So whenever you take the integral of a trig function like this, you're always going to take the antiderivative of it and divide it by the coefficient. Same thing with another transcendental function, e to the 2x. That's equal to e to the 2x divided by 2. If you take the derivative of that, you will get e to the 2x divided by 2 times 2. The 2's cancel. You end up with e to the 2x. Okay? So knowing that, first of all, what's the integral of that?
Of secant x tangent x, that integrates into, isn't that a
Secant x.
just secant x?
The derivative of secant x is secant tangent. Okay? So, using our same logic, I'm not sure why this is under u substitution. I wouldn't call this u substitution at all, but nonetheless.
So under the same logic, that just turns into secant x divided by 2?
If we take the derivative of that, we get secant 2x tangent 2x all over 2 times the derivative of the inside, which is 2. The 2's cancel.
Yeah, I guess I don't see why that's a substitution.
Yeah, I don't either. I mean, I suppose you could say, well, here's where it was substitution. You would let u equal 2x. So now we have the integral of secant of u tangent of u, but dx is going to be du divided by 2. So you could say that we could use substitution actually to solve that, but not so much. Now, the first thing to look for, we have the product here. We have the product of this times the product of that. So if we're going to use u substitution, is either one of those the derivative of what we would let u equal to?
No.
Actually it is. Secant squared is the derivative of tangent.
Yeah.
So if I let u equal what?
Secant squared?
No.
X.
We know that the if this is
Oh,
the
tangent
derivative
squared
of,
x.
well, actually just tangent x.
Just tangent?
Just tangent. Now let's work through it. I'll show you exactly why. Du dx equals secant squared x. So dx equals du divided by secant squared x. Here's this thing in the denominator. That's all we need. It's going to cancel out with that secant squared x. In other words, when I rewrite this as an integral of u, it's u squared. And then instead of, well, I've got the secant squared x and instead of dx, I'm going to write du over secant squared x. This goes away. We've got a very simple integral. Integrate it, resubstitute, you got your answer. So what you're looking for when you're looking to do integration by substitution is the product of two things, where one of the things is the derivative, not the integral, but the derivative, not necessarily of the other thing, but in this case u was tangent of x. So it was the derivative of what we would make u equal to. That's what was key to recognizing that that was a u substitution problem. Let's do an easier one first. I want to do this one.
Tangent x dx.
Notice that we have not figured out an antiderivative of this. Right?
Yes.
We don't have one. In other words, none of the derivatives of the 6 standard trig functions equal tangent of x. So we have a problem right off the get-go. So the first thing I'm going to do is convert it using sine x over cosine x. Now, what would I let u equal to? Remember that the derivative of u is going to end up in my denominator. So what am I going to let u equal to?
1 over cosine x?
Just cosine x.
Just cosine x?
Yeah. Watch what happens. Du dx equals negative sine x. So dx ends up being equal to du divided by minus sine x. So now I can rewrite my integral as sine x over u And instead of dx, I got du over minus sine x. Notice how this denominator always is in the denominator. That derivative of u is always in the denominator. And I need to get rid of sine x. I don't know how to do this integral unless I can somehow cancel out sine x. So if I know that when I substitute for dx, I'm going to have sine x in the denominator, that's the key part. Okay? Now this is equal to negative. I'm going to take out the side. 1 over u du. What's the integral of that?
That's just u to
Natural log of u. Notice the power rule. This is the one place the power rule doesn't work. If I add 1 and divide by the new exponent, I'm going to be dividing by 0. So if you find yourself trying to use the power rule and end up dividing by 0, know that the answer is natural log. Okay, that's one way to memorize it, really. So it's natural log of u, which is equal to minus the natural log of sine x. Oh, excuse me, cosine x. We let u equal cosine. So here's our answer, plus c. Now, let's examine this problem a little bit, because this is not that easy to determine. It's not always easy to figure out what you're going to let u equal here. Could we have let u equal the top? Sine x. Let's see what happens if we would have tried letting u equal sine x. Now du dx equals cosine x, dx equals du divided by cosine x. Now I've got the integral of u over cosine x, and now dx is going to be du over cosine x. Now I've got an integral I have no idea what to do with. It's got both a u and an x in it. So letting u equal to the numerator did not work. Does not allow us to solve that integral. So you always have to remember that whatever you let u equal to, the derivative is going to end up in the denominator and cancel out that. Now, I want to show you the shortcut, because you may have learned the shortcut and wondering why I'm going to all of this trouble. I'm going to let u equal cosine x, right?
Yeah.
So du equals minus sine x dx. Don't really have to solve for dx. So all I have to do is search someplace in my integral for that. And I found it. I've got it right here. So I can immediately say 1 over u, and I'm looking at sine x dx, and that's equal to minus du. So there's the minus sign, there's the du. In other words, I actually saved a couple of steps by recognizing that in my integral, I'm looking at du. All right. Let's look at this next problem, which is similar. Cosine x over sine x squared. What am I going to let u equal to?
So cosine x over sine x squared. Do you let it equal to See, I was gonna say just a single sine, just sine x.
That's
but
correct. That's
then you
correct.
It is.
Yeah, because the key is the derivative of that is cosine x, and that's what we need to get rid of. That's in the numerator. So we wouldn't want to let u equal sine squared of x, because the derivative would not any longer be a perfect cancellation of this.
I figured out what I was thinking.
Okay. So now what's the next step?
The derivative of that du dx is a negative cosine x dx.
Now let's stop right there. Let's not go any further. We don't need to solve for dx, because I can see in this integral that there's a cosine x dx, matches for that. That's what I'm looking for. I want to substitute a du for that.
Then just rewrite it as a du, or negative du over u.
Over u squared.
U squared.
Remember, we let u equal sine x, not sine squared x.
Yeah, that's what my original confusion of it was. I was thinking we get rid of one of the u's that way, and the other sine x, or one of the sine x's there, and the other sine x. I originally forgot that by replacing it, you get u squared, not.
Okay, you know how to do this, right?
Yeah.
All
Yeah.
right. Let's go on then. I don't want to waste time doing stuff that I know you know how to do, because I actually have quite a bit of material to cover today if we're going to cover all of it, which I don't think we are. There's one other kind of substitution. There's only two kinds that I know. One follows this pattern here, where you have a composite function multiplied by the derivative of the inside. These first 6 problems were all like that. Okay?
Okay.
The other kind of u substitution is this kind. Notice that we don't have that situation here. Now, again, this is doable by distributing it, so I don't really like this one. In other words, I don't have to use u substitution here. Why don't I just distribute it? And I got 6 square root of x dx minus, well, x times square root of x is x to the 3 halves dx. Now I know how to do that. That's just power rule, and that's just power rule. So I don't need to use u substitution here. So let's look at number 8, where we do need to use u substitution. Again, it does not follow that rule of the first 6 problems. If I let u equal this, the derivative is 1, not x. I have no way to distribute this. I can't multiply x times the square root of x plus 4. So how to do this? Well, it's very similar. You let u equal the same thing you would have let it equal. It's just going to work out a little different. Well, I'm still going to need to substitute. In other words, I'm still going to turn it into an integral of u. It's just that it's going to be a little different. It's not quite recognizable as a composite times the derivative of the inside. So du is equal to dx. See that?
Yeah.
Okay, so now let's see if we can write it as an integral completely in u. Well, if u is equal to x plus 4, x has to be equal to u minus 4. So there's my x. Now I have the square root of u. And for du, or for dx, I got du. I can do this by distributing.
So it's just a matter of rewriting it.
Yeah, in other words, this is u to the 1/2. Well, u to the 1/2 times u is u to the 3/2 minus 4u to the 1/2. So, in other words, I can now do with this what I could have done with number 7 without u substitution. On number 7, I don't really need u substitution. I can distribute and integrate that using the power rule, the reverse power rule. Number 8, I can't do that. I can't multiply this times that. I don't know how to distribute that. But after I use u substitution, it turns out to be an integral in u that now I can distribute this. It looks more like number 7. My square root is of a single variable, so I can distribute that with both of those terms and then integrate. Number 9.
That looks a
What do
little...
you recognize about number 9?
Number 9.
It's the product of two things, right?
Yes. Isn't the,
What's the derivative of the inside thing?
2x. The inside.
So, this fits u substitution of the first kind, right? Because the derivative of the inside is going to eliminate this x. So, you take it from the get-go. U is equal to what?
U is equal to 1 plus x squared, and then that turns into du dx, which is 2x, and then 2x dx, and then you want to, yeah, and then dx is equal to du over 2x, so we can rewrite that. Cancel the
We don't
x.
need to. Let's start doing it in a more sophisticated way. Now, to do it this shortcut way, which is 2 steps earlier, it is necessary to think out of the box a little bit. In other words, I'm looking for a 2x dx. Do you see it in that integral? I see an x dx.
You just moved it.
Yeah,
Yes,
I see an x dx, so if I'm looking for a 2x dx, this is what they generally do. They multiply by 2 and do that. I didn't change anything. I put a 2 inside the integral, I put a 1/2 outside the integral. Now, I've got my 2x dx. So now, what's the new integral look like?
U, or du times u to the 1/3.
Yeah. And you know how to do that.
Yeah.
Okay. Let's do number 10. Now notice, this is cosine of x squared, not cosine squared of x. They're not the same.
So,
what am I going to let u equal to? What u would let its derivative be in the numerator already?
x squared?
Yes. Now,
Then we do
I'm going to do the same thing. I'm going to put a 2 there, take a 1/2 out. So there's my 2x dx that's over here. So it's cosine of u squared, cosine of u du. What's the integral of that?
Sine of u
Which would be sine of x squared.
squared.
So this whole thing is sine of x squared all over this 2 from the 1/2 over there.
Yeah.
Okay? So 10, the only one of these problems really that required us to use the second type of u substitution was number 8. Number 7, I didn't need u substitution at all. Number 9 was of the first form, this form here, where we had a f of gx times a g prime of x. And so was number 10. So number 9 and 10 were the first kind of u substitution. Now, sometimes you want to use substitution even if you could distribute it out and not have to use substitution. For example, 11. I mean, I could always take that thing to the 4th power and all the effort that would be entailed, but that'd be a lot of work. If I think of this as being like u substitution, what am I going to let u equal to?
1 plus 6x.
What's the derivative of that?
6.
I've already got my 6dx right there. So it very easily turns into u to the 4th du.
Which is easy to do.
Much easier to do than to multiply that out 4 times and then integrate those 4 different integrals. All right, all of these problems look to me, let's just not do them because I'd like to go on if we can, if you want to get to the second document at least. Let's just look at them. Notice the derivative of the inside is 2x. There's the 2x. The derivative of the inside is minus 2x. There's the minus 2x. The derivative of the inside is minus 8x. There's the minus 8x. They're making it really easy for you. They're not even putting an extra constant in there. On number 17, the derivative of the inside is 3x squared. So all we care about is a way to get rid of that x squared. We can handle the 3. That'll come out as a 1/3. Still fits the general definition of a composite function times the derivative of the inside. Same there, same there, same there, same there. Even when u is in the denominator, we are still looking for its derivative in the numerator. So the derivative of u here is minus 2x. That's fine. It's going to end up in the denominator when we go through the long method, and that'll get rid of that x there. So none of these are particularly difficult if you understand the method. There is one that's slightly different, and that's when natural log comes about. Because when you take the derivative of the natural log, it's 1 over x, and it ends up in the numerator, not the denominator. In other words, let's do that one. Notice this does not fit the definition of what we're looking for. We've been looking for the derivative of u, if we let u be natural log of x, we're looking for the derivative to be in the numerator, and it's in the denominator here. But because it's natural log, that works out perfect. That's what you need for natural log. Watch what happens. So here, dx ends up being equal to x times du. That's perfect. That's what we need. We got the integral of u du. In other words, when we're going to let u equal a natural log of something, then we need that other pesky variable to be in the denominator, not the numerator. And they didn't give you any. It's the reverse. It's the reverse. It's because the derivative of natural log is 1 over x. So by the time you solve for dx, you've got this x in the numerator, not the denominator. Notice 29. Let's do 29. It's a little harder than most.
Yeah, that is an interesting question.
Always start off by saying, well, what would I let u equal to?
Would you let u equal to the 1 over t squared?
No, don't. Start off with the more obvious. In other words, if I let u equal this, well then this whole thing turns into u cubed. I know how to integrate that. The question is, will I get rid of this 1 over t squared? Might. Only because the variable's in the denominator over here, that probably means it's going to end up in the numerator by the time I'm done, right? What's du equal to? U is equal to 1 plus t to the minus 1. So what's du equal to? Chase, you still there? Chase, I think I lost you. You back?
Hello?
Yeah, you're back. Every now and then
Yeah,
I lose your audio, and then you come back.
My internet connection's going to...
Yeah, that's okay. This problem is going to work, even though it doesn't fit the normal mold. In other words, normally we're looking, it actually does fit the normal mold. It's just kind of in reverse. Let's find du. If u is equal to 1 plus t to the minus 1, what's du equal?
du is negative 1 t to the negative 2.
Right?
dt.
Multiply by the exponent and subtract 1. Biggest thing you have to keep straight when you're doing differentiation and when you're doing integration. I know that's tough when you're first learning integration. But the problem is most integration is half integration and half differentiation. So you're always doing some of both. Okay? So if du is equal to that, dt is equal to du divided by minus t to the minus 2. Well, that puts the t to the minus 2 in the numerator. Perfect. That's where we need it. to get rid of that t squared that's in the denominator. So I'm going to take out that negative sign. I'm going to have u cubed. And then I'm doing this the long way. In place of dt, I'm going to write t squared du. Over this t squared from the problem, the t squares cancel, and you end up with a very easy integral. I know you know how to take it from there.
Yeah.
So most of the time we're looking for the thing we need to get rid of in the numerator. In other words, on problem 28, the inconvenient variable is x cubed. That's what I need to get rid of. Well, the derivative of u is going to be 4x cubed. That'll get rid of it because that 4x cubed will end up in the denominator. Well, this is slightly different because when I let u equal 1 plus 1 over t, the derivative of that is t to the minus 2. So my t squared actually ends up in the numerator instead of the denominator. But that's perfect. That's where I want it. A little bit like the natural log function. I don't even know why 30's in there. We wouldn't use u substitution for 30 under any circumstances. I'd break 30 up into the integral of x squared plus the integral of 1 over 9x squared. Use the power rule on it. Same with 31, same with 32. Don't need u substitution for either one. Notice 47 is a variation of the integral of sine of 4x. That's all it is, which was minus cosine of 4x divided by 4. Well, the pi is a constant. I can take it out immediately. So I'm really taking the integral of the sine of pi x. That's going to be the minus cosine of pi x divided by pi. .48 is our classical u substitution. 49, by definition, that's going to be minus cosine of 4x divided by 4. This is going to be 50 is going to be cosine of 8x divided by 8. All right. Well, we didn't get into your second document at all.
That's fine.
Yeah, I think it's still worthwhile. And let's see. Oh, the trapezoidal rule and Simpson's rule. Yeah, that. Let me just say one thing about why all of a sudden we're looking at trapezoidal rule. Why are they going backwards here and looking at approximation techniques when we're learning how to integrate precisely? Well, the answer is that sometimes you will get a function that there's no way to integrate. There is no function on the planet whose derivative is this. So you can't find an antiderivative for that function. And there's a lot of functions that there is no antiderivative for. Well, when you don't have an antiderivative for a function, your next best technique that we've come up with is approximation using various techniques. Trapezoidal rule. Trapezoidal rule finds out the area of the curve under the curve. Instead of breaking it into rectangles, breaks it into trapezoids. Seems like it would be more accurate. It is. Simpson's rule takes it a step further and breaks it into parabolas at the top, shaped either concave or convex to match the curve. So Simpson's rule is one of the most accurate approximation techniques yet. But that's why they're still talking approximation techniques, because there simply are some functions that there is no integral for, and you have to use an approximation technique.
Okay.
Okay? All right, Chase. Have a good one, and I will talk to you next Saturday. Okay?
Talk to you next Saturday.
All right. Bye-bye.